right, so this, these are the symbols that we use to dictate set membership. This kind of, it's sort of like a squishy E, right? I mean, it's, yeah, but it's an E for element. This means is an element of. And when you put a line through it, it means is not an element of. Okay. All right, so R is an element of the alphabet. Right? That's true. Okay. 7 is not an element of 1, 2, 3, 4, 5.
False.
True, because it's...
Wait, 1, 2, oh, there's not the dot. Okay.
Yeah. Because it ends, right? If it went on forever, it would have been false. The set A is an element of AB.
False.
This one is false.
Okay.
And here's why. Because A is an element
Yeah.
of the set AB. But the set A is by itself, right? So the set A would be an element if I had a set thing in there, like that.
So pretty much if there's a set outside of where it's saying is an element of, and there's not another set inside that set,
right.
then it's just going to be...
Yeah, so you'd have to have a set inside the set like this for that to be true. Whereas here, this is just an A. This is not the set A. Mention it now. Just on like a little side note, the empty set, so basically nothing, is pretty much not an element of any set. Okay, and the reason it's not an element is because it's going to be called what we're going to go over in a little while, called a subset. So an empty set is not an element of some set, like with stuff in it. Okay.
So anything that says empty set.
All right, so we have the set of natural numbers. These are also known as counting numbers. So if you hear counting numbers and natural numbers, those terms are interchangeable. Its symbol is like a bold N or an N like this with a second kind of a crossed line, because a lot of times when you're handwriting it's hard to bold. Okay, and basically what that is when you start counting, where do you start? You start at 1. So it's 1, 2, 3, 4, 5, forever. If we want to express each of the following sets using the roster method, set A is the set of natural numbers less than 5. Now the reason we can use the roster method is because we're saying natural numbers. They start at 1. There are no negatives, there are no zeros. So you couldn't list like the set of numbers less than 5, because that would be every decimal, every fraction, every negative that was less than 5. You can't possibly list that. But we can list the natural numbers. So we say A, and that's 1, 2, 3, 4.
If we forget to put the A equals, are you going to count that wrong?
No, I'm going to put a big red A equals and put an arrow, and don't forget. Okay. Set B is the set of natural numbers greater than or equal to 25. So set B. So greater than or equal, that means we include 25, 26, 27, and that's going to go on forever, right? So we're just going to do 3 dots and close our set. And then we have set E is the set X, all X, such that X is a natural number and X is even. So even 2, 4, 6, 8, and that goes on forever as well. Alright, so we need to talk about some inequalities and set builder notation, and I didn't put any lines on here because I figured you'd want to space it out yourself. So just kind of break this into thirds. This one can be smaller. So here we have the inequality. This is what you would write in set builder notation. That's an I. And this is roster. Okay. So if we have X is less than A. Okay. So that would be X such that X is a natural number and X, sorry, let me actually write the word and. X is less than, let's just say it was less than 4. Okay. Well, that would be 1, 2, and 3. Okay, if we said X is less than or equal to A, so that's X such that X is an element of N, and X is less than or equal to 4. Well, if it's less than or equal, it includes that number. So it includes the 4. Okay, if X is greater than A, we'll say it's greater than 4. You don't start at 4 because it's just strictly greater, so you start at 5, 6, 7, forever. And then if it's greater than or equal, and you'll notice I'm always putting that it's a natural number, because if it's not a natural number, if it's an integer or a real number or a rational number, this is going to be different. So right now we're just dealing with natural numbers. And the reason natural numbers is because they're much, much easier to deal with. There's a lot less of them. Okay. These are fairly straightforward, but what about when you have a situation like this? A is less than X is less than B. So maybe 4 is less than X is less than 8. So we don't include the 4. So we have 5, 6, and 7, and we don't include the 8. And if you're running out of space, the next page also has a blank box for you to continue on. If I have A is less than or equal to X is less than or equal to B, so we'll do less than or equal to 4 is less than or equal to X is less than or equal to 8. So in this time, you're actually going to include 5 comes after 4, not 6. So you'll actually include the 4 and the 8. Sometimes you get a mixture. So here I have a less than or equal to, and here I just have a less than. So if that happens, it includes the 4, but not the 8. Or it can go the other way. And in that case, it would not include the 4, but it would include the 8. So we're going to express using roster method.
This packet is confusing.
You should have another blank. If not, you can maybe fit it in the margin or something. Okay. So we have x is a natural number and x is less than 100. Well, natural numbers start at 1 and go up from there. And do you think I should list all 100?
Yeah.
Really?
No.
There you go. I listed all 100.
Good job.
Okay, now this one is going to be slightly different. It's not going to include 100. So what do I do? 99. Yeah. Because it's a natural number, so the last number before you get to 100 is a 99. So this one will go only up to 99. Basically, that's the number of elements in a set. Okay, and we indicate cardinality. If I wanted to say the cardinality of set A, it would go like this, and then I would have some number, like I'll say maybe if set A has 10 elements in it, so it would be the cardinality of A is 10.
So the symbol of cardinality is always the little n.
Yeah, this is the symbol of cardinality right here. So that is this. And that would be a set, if I had some set A that had ten elements in it. Okay. If we have repeating elements, so let's say I have 1, 1, 3, 4, 6, 6. Okay. My cardinality, the repeating elements don't get counted. So I have 1, 1, but I only count that once. 1, 2, 3, 4. So I don't count the second 6 either. So the cardinality, if this was like set B, the cardinality of that set B is going to be 4. Even though it looks like it has 6 things in it, but a 1 is a 1, right? So I don't count it twice. No, don't get counted. So they don't get counted more than once. Okay. So here we have this set A, and we're going to determine its cardinality. So I have 1, 2, 3, 4 elements, so the cardinality of A is 4. B has, yeah, 1. Okay, now I didn't list all of the elements, but I'm going between 15 and 23 or 22 here, so I had to do, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's 11. And if I have an empty set,
So the cardinality is 0?
yep. If you have an empty set, there are no elements in it, so your cardinality is 0. Okay, so equivalency. Okay, equivalent and equal are not the same thing. Okay, 2 quarters are equal, but a quarter and then 2 dimes and a nickel are equivalent. Does that make sense? So like the quarters are equal because they're the exact same coin. The quarter is equal or equivalent to 2 dimes and a nickel. They're not the same, but they have the same value. And so that's what equivalent sets are like. They contain the same number of elements. So they have the same cardinality. Because, a bunch of different sets can have the same number of elements in them, but they're all different, right? But they're equivalent because they have the same number of elements in them. So what you'd have is the cardinality of A would be equal to the cardinality of B. And that would mean that these sets were equivalent. Okay. So an example of that, if I had the set A, which is X such that X is a vowel, well, that means that we have A, E, I, O, and U. And we're going to skip the sometimes Y. And then if I had set B, X is a natural number, and 3 is less than or equal to X is less than or equal to 7. Well, that set would be 3, 4, 5, 6, 7. Cardinality of A is 1, 2, 3, 4, 5. Cardinality of B, 1, 2, 3, 4, 5. So these sets are equivalent. I can take these and I can draw little arrow or line connecting, and they go 1 element each, right? So this is 1 to 1, 1 to 1, 1 to 1. Okay, if you remember it all from the past, 1-to-1 correspondence means that for every 1 in this group over here, I have 1 that I can pair it with in this group over here. So we're going to talk about that a little bit. So if the elements in set A can be placed in a 1-to-1 correspondence. So with the elements in set B. Okay, so if I tell you 2 sets are 1-to-1, then you can say, okay, they're equivalent. Okay. If they can't be, Now we're talking about all of the elements, right? It has to be every element in set A is in a one-to-one correspondent with every element in set B. That's also called being onto. So it's one-to-one and onto.
Wait, 101 and off. That's every other one.
All right, so we have
That was easy.
this chart that they gave us. They had like this whole graph, and I just took the information out of the graph. And they say that women prefer men that are older and men prefer women that are younger. And in Zambia, women like men to be about 4 years older than them, but men like women to be about 7 years younger than them. So I don't know how that really works.
Wait a second.
That's Zambia.
Zambia's weird.
In Colombia, they're about equal, so that works out really well. Women like men to be about 4.5 years older, and men like women to be about 4.5 years younger. Poland, women like their men about 3 years older, and the men like their women about 3 years younger, so that works. Same with Italy. And then the United States, it's about 2 and 2, so that works as well.
I know what's going on with this.
Okay, so here we have, we're going to see, we have a set of the countries, right? So we have these 5 countries, and then we have a set of the average number of years women in the countries prefer men older than themselves. So we're going to let A be Zambia, Colombia, Poland, Italy, and the United States. And we're going to let B be the ages. So we have 4.2, 4.5, 3.3, 3.3, and 1.9. And here's how we're going to tell if the sets are equivalent. In Zambia, they like them to be 4.2. Colombia. Oh, wait. I messed up. See, here I go. 3.3 is the same number, right? See, we don't count it twice.
But couldn't you just put it into the set twice and just not count it twice?
Well, remember when we talked about equivalence, it's about cardinality, and when cardinality, you don't count the same number twice.
Okay, so now
Yeah.
you can have the ones. Okay.
Poland likes 3.3. Italy likes 3.3. Look at that. I have 2 lines to the same number.
Because
These are not equivalent. Now, if I had listed both 3.3s, I would have messed up, right? Because I would have said Poland, Italy, US. Yeah, that's good.
That's gonna
Except for you can't count this. So this set actually only has 4 elements in it. 1, 2, 3, 4. And this set has 5. So the cardinality of A, cardinality of B is 4. Here. Okay, so we have different sizes of infinity. Okay, natural numbers are the counting numbers. 1, 2, 3, 4, 5, 6, 7, and goes on forever, right? It's infinite. It goes on forever, but what's it missing? It's missing all of the negative numbers. It's missing all of the fractions, the decimals, the imperfect roots, the decimals that never end, never repeat, right? There's a lot of things that are not missing, or that are not there. So that's a smaller infinity. I mean, it's still infinite, but it has less things in it. The next set of numbers is called the whole numbers. That's 0, 1, 2, 3, 4, 5, 6, 7, right? So it's infinite with one more number than the natural numbers had, because we added a 0. So it's a slightly bigger, it's bigger by 1, infinity.
Are we gonna have to draw this fancy in-looking thing with the 0? I know you just said the name of it. but-
Aleph,
Aleph?
Aleph,
Like Aleph?
A-L-E-P-H.
Ooh, is it-
Aleph.
Aleph.
That's
It's like a
the
line.
Hebrew letter Aleph. Okay, now think about the integers. You guys know the integers are all the positive and negative numbers, right? And 0. So that set of infinity is about twice as big as the natural numbers, because you have all the positive numbers and all the negative numbers. And then you have the rational numbers, which includes all of the fractions and the decimals that end in repeat. So that one is even bigger. Then you have a set over here by itself called the irrational numbers, and those are all the non-ending, non-repeating decimals. They're also infinite, but it's kind of hanging out by itself, so it's actually smaller than the rational numbers because it doesn't include any ending, repeating decimals or fractions or whole numbers or negative numbers. And then all together, that all fits inside the real numbers, which is the biggest infinity. So does that make sense how you can have different sizes of infinity?
So wait, when the 0 is on the...
So this is the symbol for the natural numbers, right? So you have this infinity is smaller than the whole numbers, which is smaller than the integers, which is smaller than the rational numbers.
Wait, what? No.
Yeah.
You...
So this 0 is the natural numbers.
Are we already supposed to know that 1 means something? And
No, I'm right. I'm saying it. This is the whole numbers.
Mm-hmm.
This is the integers.
Mhm.
This is the rational numbers.
Okay.
So whole numbers.
On the test, is it going to say that?
No, you're not gonna have this on your test. I'm
Oh,
just
Shit.
equal sets are not the same as equivalent sets. Remember we talked about quarter is equal to quarter. So equal sets are equal if they contain the exact same elements.
So basically, you'd have to have the same formula, like the same equation for each one. Like A and B have to have the same equation for them to be equal sets.
Right, or they have
Or,
to be
like, they
the
have a
same
weird-
group of
Yeah.
like 1, 2, 3, 4 and 1, 2, 3, 4.
Yeah.
So you write that with an actual equal. Whereas before we wrote n of A is equal to n of B, that's when they're equivalent because they have the same number of sets. That if they're equal, they have the exact same elements. So again, it's like a quarter is equal to a quarter, whereas a quarter was equivalent to 2 dimes and a nickel.
Okay.
We have 4, 8, 9, and a 4, an 8, and a 9, so that's, yes. I have 1, 3, 5, and 0, 1, 3, 5. No. It's that simple. Just look at your sets and do they have the exact same things?
Do they match? No. Done.
Yes. You've been doing that since,
Ever?
well, you remember on Sesame Street where they said which one of these things doesn't go and they'd show, yeah, the 4.
You didn't watch
No?
Sesame Street? How old are you?
Yeah, you sang the song. Which of these things goes with the others?
You did not
Yeah.
watch Sesame Street.
Okay.
I was a sheltered child.
All right, we do.